everyone. Welcome to another virtual Urban Health Club session. This week, we will continue our STEM series with a focus on chemical reactions. We will be focusing on a Chicago Public School chemistry independent project. So today's topic will be staying home and slowing the spread.
All right, so our first activity is going to be called the vinegar soda experiment. This is a quite simple experiment you can carry out in your kitchen. Some of the materials that you will need are vinegar, baking soda, water, 2 to 5 little containers to hold the solutions, a baking sheet or tray, or you could even use a plate to hold the individual containers. And if you guys look on the side, we have we've made a chart for you guys with 5 individual trials. Each trial has different amounts of reagents that you're going to be using. And essentially what you guys are going to be monitoring are the gas being produced. So the bubbles that are being produced when you add all the reagents together. On the next slide, it shows an example. You could follow this video just to see if you are adding all the reagents correctly. This one, however, is basically showing what dish soap does to the reaction, and it actually helps it get carried out. So in essence, it acts as a catalyst for the reaction to take place. Catalysts help reactions get carried out. And there's plenty of catalysts that are naturally occurring, a lot of chemical reactions that happen in your body. Essentially, what you guys could also do is, if you want, you could mix with certain conditions. A lot of scientists will either put the solution in cold environments or hot environments to see if that affects the reaction, or they could manipulate the pH of the solution, a lot of different conditions.
All right, y'all. So the collision theory of chemical reactions is what it sounds like. It's a way of explaining how chemical reactions work. And it's talked about in the high school level, of course, but also in the college level, even the medical school level, graduate school level. It never really goes away. And I feel a lot of people think of it as this really complicated thing, but I actually think it's pretty easy. And here's how I think about it. So you remember when you were a kid and you'd go to the park and blow bubbles, and some of those bubbles would crash into each other and kind of combine to make one big bubble, or even, do this like double bubble thing that, it's just like this, this really weird looking thing just floating around. Well, so bubbles crash into each other and combine and make something different. And it turns out that's how atoms make chemical reactions too. Atoms do the exact same thing. So atoms can crash into each other and make something different. And that's how chemical reactions happen. So that's a basic idea of the collision theory of chemical reaction. There's a little bit more detail that goes into it, which this video will help explain. But once that's done, we'll go through those together.
Here's a beaker of cold water and a beaker of hot water. When you add sugar cubes to them, the one in the hot water will dissolve faster than the one in the cold water. To explain the different rates of reactions, Max Trotz and William Lewis came up with collision theory in the early 1900s. The first assumption of collision theory is that the particles must collide with one another in order to react. Most particles will act like billiard balls in a game of pool, and when they collide, they bounce off each other. The collision itself isn't all that's needed for a reaction to occur. The particles also need to have enough energy, enough speed, to break and form new bonds when they collide. The minimum energy required for a reaction to occur is called the activation energy. Some reactions require very little, and some need a lot more to get started. Generally speaking, most reactions will occur faster when the temperature is increased, because temperature is the average kinetic energy of the particles. With more kinetic energy, they will be more likely to have enough activation energy for the reaction to occur. But for some reactions, there is still one more factor: orientation. Even if the particles collide with sufficient speed, if they aren't at the correct angle, a reaction won't happen. In this example of nitrogen monoxide and ozone, the reaction didn't occur because the oxygen of each molecule touched during the collision. In this collision of the same two molecules, the nitrogen touches an oxygen and the reaction occurs, making oxygen and nitrogen dioxide. The orientation was correct, so the reaction could occur. So in summary, the three key ideas of collision theory are that particles must collide to react, they must have sufficient energy to break and make new bonds, and they must collide with the correct orientation. Thanks for watching this episode of Teacher's Pet. Don't forget to like and subscribe and follow me on Twitter at SciencePet.
All right, so as you guys saw in the video, when atoms crash into each other, if they have three things going for them, so if two atoms that are reactable crash into each other, right? So collision is needed. They also have the right orientation, and we'll talk about that more in a bit. They have the right orientation, and they also have the sufficient amount of energy required. They can crash into each other and combine and bind to each other and make a molecule. So that's what is happening at the very basic, really small little atomic level. And so we already talked about, like, the collision needing to happen in the example of the bubbles. But there's these other two things too that need to happen. So they need to be in the correct orientation. So they need to be like in the correct position when they crash into each other to react. And they also need the right amount of energy to react. And the way I think about this, I also think this is pretty easy to understand, because the way I think about this is bowling. So if you want to get a strike, right, when you roll the bowling ball towards the pins, the bowling ball has to hit the right position, and it also needs to be going fast enough for you to get a strike. So let's say that you throw the ball, and you don't throw the ball, but you roll the ball really fast, and it hits the pin all the way on the left. Well, it has the right energy, but it didn't collide in the correct position. So you're not going to get a strike like that. But let's say you roll the bowling ball and it's at the right dead center and the right position where it needs to be for you to get a strike. But if you just granny roll that thing and then it's going like 2 miles an hour, you're not going to get a strike either. So chemical reactions behave the same way. So first, atoms need to crash into each other, right? And they need to be going at a particular amount of speed. So they have to have the required amount of energy. And they also need to be in the right position when they collide. And if all those things happen, if all those three things happen, then you get a chemical reaction and they form a molecule. So that's the collision theory in a nutshell. Hopefully it's not too bad. Just think about like bubbles and bowling. That's how I think about it, and it should make sense. So that's what's happening in the experiment that was shown in the first couple of slides. So you have the baking soda molecules and you have the vinegar molecules just crashing into each other, and they make a reaction, right? So using that knowledge of like the molecules crashing into each other, let's think about how we can modify those things, how we can change those things up to affect the reaction, to affect the final product. So if we wanted to slow the rate of a reaction down, what can we control? Out of those three things, what can we control? So we can probably control the amount of collisions happening, right? Because if we put more or less baking soda or vinegar into the reaction, then that will increase or decrease the amount of like product that's being made, so the amount of chemical reaction happening. So as it says on the second bullet point, if you add more water into the vinegar, that's going to decrease the rate of reaction. So this makes sense, because if you have like a given amount of baking soda, given amount of vinegar, and you just dump a bunch of water into that thing, the molecules of the vinegar and the molecules of the baking soda, they're going to have to like sift through all the water. They have to like make their way through like, you know, all the water molecules to find each other and react. So you're not going to have as many collisions between those two things. The second thing is you can heat up the reaction or cool down the reaction, and those things will speed up or slow down the reaction. So bonus points if you can see where I'm going here. But if you heat up the reaction, it's going to have more energy. And so if you have more energy, the things are going to happen faster. So by heating up the reaction, of course, you make it faster. By slowing it down, by cooling it down, you'd slow it down. So yeah, that's the basics of the collision theory, and my friend Ravi will help talk through the rest of the details here.
Yes, like Jeremy was saying, the collision theory is pretty intuitive. So yeah, you know, a lot of the stuff that we're going to talk about now is just things that make sense if you think about it. So on this slide, we're going to talk about some of the different factors that affect the rate of a chemical reaction. So the first one we're going to talk about is the concentration of the reactant. So like in the baking soda and vinegar example, the more baking soda you have and the more vinegar you have, there's going to be more collisions between those two molecules. And that makes sense intuitively. The more stuff you have, the more likely it is that they're going to bump in together and that something will happen. And so that's what the slide says. So the first thing that you can do is you can increase the concentration of your reactants. As a consequence of that, the rate of the reaction will increase. And then why? It's because you have more things that can collide. The second thing is the temperature. So like you guys saw in that previous video, by increasing the temperature, you're decreasing the amount of activation energy needed to initiate the reaction. And that kind of makes sense too if you think about it. The more you heat it up, the more the particles are going to move around with each other and randomly bump into each other. And the more collisions you have between the particles, the faster the reaction will happen. And that kind of makes sense too if you think about it. If you heat up the baking soda and vinegar, it's more likely that the reaction is going to proceed faster. The other thing is surface area. So again, another really important concept in biology and chemistry is that as you increase the surface area, you have more opportunities for collisions to happen. And so that's what's going to happen too. So if you, for example, imagine if you took a baking soda, but it was still in chunks. So if you're dropping the chunks into vinegar, it's less likely to react as well as if you turn it into like a powder. And so by turning it into a powder, what you've done is increase the surface area. It's the same thing like when you're trying to dissolve sugar in water, you don't just drop chunks in there, you turn it into smaller particles and then it dissolves a lot easier. And so it's the same thing, you know, as you increase the surface area, there's more opportunities for the molecules to collide with each other and then for the reaction to proceed. So yeah, you know, these are just a couple of the different factors that you can influence, and a lot of it's very intuitive. So if you just think about it, you'll probably be able to figure out what'll slow down a reaction and then what'll speed it up as well. And then here's a video. It's 3 to 4 minutes long. It kind of talks about some of the things that we've already mentioned. But if you want just something to depict everything that we've been saying visually, highly recommend watching that video.
So for the following activity, we'll start to talk a little bit more about how one of the most important guidelines to what's currently going on, social distancing, how that plays a role in terms of flattening the curve and how that relates to chemical reaction. If you click on the article, you'll have like a breakdown in terms of various scenarios that have varying conditions, one of which being social distancing. So for the next slide, we'll talk a little bit more. We'll have like a visual representation in terms of what was previously talked about in terms of various conditions, either slowing down or increasing the rate of reaction. As you can see, this is a video that is visualizing social gatherings. On the left, you have minimal social gatherings, and on the right is more social gatherings. As you can see, the one on the left, it didn't go up as high, but on the right, you had that exponential reaction. A key thing to see to note is you see that the way that this video was edited, it was sped up to 10 times the speed. You can sort of think about that as reaching or steepening the curve and how long it takes for it to sort of go down. So for the next slide, it's another video that goes that visualizes that same concept of why is it important for us to social distance. So you have these two vials. The one on the right is diluted. It was diluted to represent us social distancing, but in this terms, it was diluted to decrease the concentration of the substance. As you can see, once the reactants were put into the vials, there was minimal a minimal reaction for the one that was diluted, but for the vial that was just completely only hydrogen peroxide, you noticed how it exceeded those brackets, or that limitation that represented the capacity of space that hospitals have during this time. To sort of end this activity, it would be important for us to spread this knowledge somehow. So if you can find ways to incorporate what you learn in a fun, active, engaging representation to just spread. You can create like an infographic or a pamphlet that pretty much talks about your connection, other connections that you're making between social distancing and what you're learning in terms of chemical reactions.
All right. Okay, so activity 4 is just a reflection of what we just learned and what our wonderful leaders just told us. So the first one we need to reflect on is, what do you know that you didn't know before? So this could be about the collision theory. This could be about the graph that that Sergio just told us about, which we're gonna go into more detail in the next slide. The second one is, how did thinking about collision theory help you about the effect of social distancing? And then just like Robbie said, you could take into like the temperature and how it speeds up and slows down like the reactions. And then number 3 of our reflection questions is, what might you do to help your friend and family understand the importance of social distancing? Now, social distancing is extremely important, and it's basically the only reason and it's basically what everyone is talking about nowadays. So I suggest you guys definitely make sure you guys are keeping your family in check on why it's important. All right, so we're going to talk a little bit more about that in the next slides too. All right, so this video is basically, I hope you guys do watch this video. We're not going to go over it right now because it's kind of long, but it's basically just telling you about the graph that Sergio did go over briefly. So on the y-axis, we're going to have the number of cases, of total cases that have COVID-19, and then on the x-axis is just the time period since the first case was discovered. So the pink one, which is the bad one, the reason why it's bad is because there was a big spike. So this could happen simply because people did not follow the rules, such as social distancing. And this happens because there's more cases. And if we were to imagine there be a middle line between the bad graph and the yellow, which is I don't know what it says, but the yellow graph, it's our capacity of hospital beds. So if we are past our capacity, there's going to be obviously more people that are going to die simply because we can't treat them, or we just can't have them in the hospitals. And then in the bottom one is just people, and the yellow one is basically people with the protection, and we're able to treat them simply because we have the capacity. Now there could be, the bad one could have the same number of cases as the the yellow one. However, the bad one, it's worse simply because, like I said, we don't have enough beds, so it increases the chances of more death rate. All right, and then, all right, so why is soap our best weapon against the coronavirus? So the reason why is simply because we don't, in the beginning, we didn't really know much about coronavirus. And soap has like this, what's it called, like this, so it works like, soap is basically a molecule. It has like two different like ends, has a polar head, and then it has a non-polar head. So when it's combined with grease and oil, it basically just clusters, and it's able to break down that grease and oil, which allows us to wash off the virus and bacteria and all that bad stuff that we have in our hands. Now, a lot of people are using hand sanitizers nowadays. However, we need to make sure that it's 60 to 65% higher in alcohol. So make sure if you guys are using your hand sanitizers, just check your alcohol level. And when we use hand sanitizers as well, make sure you're only using it because you don't have the option of using soap and water. And yeah.
Thank you so much, Diana. Thank you, all of the coordinators. We hope today's session was informational. If you have any questions or comments about the content that we discussed today, please send us an email. Our email address is uic.urbanhealthclub@gmail.com. And you can also follow us on Instagram, and our handle is uic.urbanhealthclub. Thank you so much.